Very good afternoon. So my name is Pei Seng. Welcome to be here. Before I start my session, I want to briefly introduce about myself. I'm the senior R&D engineer in VShops Corporation Berhad. So my domain actually is on in deep learning, specifically in the computer visions. And of course, just now I think I mentioned that I do some NLP works. Mainly still in the computer vision. I've been working in VTrox around 5 years. So if you have any question about deep learning implementations in computer visions, welcome to ask me later. In terms of my academic backgrounds, I was graduated as a mechatronic engineer in UTM, and then after that, I went to USM for my master's. So I'm doing something like data science analytics. Then after that, currently, I'm actually the PhD student in UTP. So my research topic actually closely related to renewable energy and also a power system control. So later I'm going to present one of my work actually is using the Explainable AI in the power system control. In terms of my professional qualifications, currently I'm a TTT certified trainer recognized by the HRD Corporation. So sometimes I actually organize trainings, and currently I'm the MBOT recognized professional technology as well. So this is a machine learning life cycles. You also can say it's a machine learning workflow. So normally how the practice start is that first you are going to ingest the data. So basically collect data and then ingest the data. Then after that you try to do data versioning because you want to track how this data being split, how it can be cleaned, and so on. After you're going to do a data versioning. I think this flow is quite standard in the machine learning operation or ML ops. And then after that, you're going to verify your performance of your data, whether is it good or bad in terms of qualities. So you're actually doing the data validations. Then you're going to do pre-processing after you train your models. So this one is quite standard. And after that, you train your models, then you need to validate your models. So you want to know whether your model is performed. Is it actually like what you expected? And then after that, you are going to deploy your models. And then after that, you label a new data again, and then you repeat this process again. So I think today my talk is actually focusing on the model validation. So what is the purpose? We want to validate our model performance. So actually, why we want to do this is because we want to achieve something called trustworthy or responsible AI. So you want your models to be it won't harm people, and then it will be performed actually what you say it actually like what you expected. So in terms of the criteria, how do you measure whether this AI or the models is trustworthy or not or responsible or not? Actually there are a few perspectives here. First, you want your model to be secure and also privacy means that it won't tell something like something secret. For example, like today I think all of you are dealing with LLM, and so on. So you want your model won't leak your personal information, although they use your information for trainings. So the privacy is very important and it must be secure. And the second one is on the reliability or privacy. So reliability means that you want your model able to do the prediction under the conditions that even is not something you expect. For example, like because currently in model you are doing the model training, right? Probably you are going to collect the data for the past 3 years or 3 months. But normally when you do a training, this model may not last long because of covariance shift or data drift, and so on. So in this case, you want your model to be robust enough. So that's why you are concerned about the reliability and as well as the safety. And the third one is transparency, which will be our focus today. So we are going to discuss it in the perspective of explainability and also interpretability. And the fourth one is known as fairness. So fairness, I think a very good example is on the bank loan approval. So like today, is there a sex discrimination there or not? Probably if you are male, then I should approve your loan, and then female I should not. So you need to if you train a model something like this, like the loan approval, so you need to really take care about fairness. And last one is the accountability. So these are the 5 aspects you want to study, when you trying to verify your models performance lah, okay, to validate your model performance. So I think okay, it's very clear. We are going to discuss on the transparency, okay, which is explainability and also interpretability. Okay, so what is explainable AI? XAI basically is a set technique introduced to help you to understand the predictions made by the model that you have developed. Okay, and with the XAI, basically what you can do is that after you understand okay what the model is doing inside, then you're able to debug and also improve the performance. So if you can see at this region, not sure this pointers. Okay, so if you look at this, so this is a standard process without explainable AI. So you got a model data set, a medical data set, then you train a deep learning model. So I will call this model as a black box AI. So why I name this as a black box? Because you know what this model actually learning. Okay, what type of is it a function? I mean, I don't know whether what is the function is inside. So I will call this one as a black box AI. So after you train the model, then you put a sample image into as a inputs, and then it tell you the result. Okay, so in this case, for example, like COVID-19, okay, it will tell you, oh, this guy is infected and this guy is not, based on the. But okay, you don't know why this model able to make these decisions. And then another question is that, can you trust this model or not? Actually, you don't know. So this is why the explainable AI are trying to coming in. So okay, so when you use explainable AI, currently we got commonly there are two types. Okay, the first one is called as a post hoc explainable AI. So what is post hoc explainable AI? Means that you train a model, then you use another techniques to study this model whether is to validate this model. So this type of technique is called post hoc explainable AI. And then there are something called intrinsic. Intrinsic means that there is an explainability capability inside the model. So for example, decision tree or linear regression. So if talking about decision tree, so the decision tree, the issue is that you can, the good thing is that you can form the if else rules. For example, if this A happen, then B is 1. So if you're using decision tree, definitely you are able, this model is able to explain something or it can be interpretable easily. So in this case, I would say decision tree is a interpretable model or intrinsic SAI model itself, because inside the model it already contains this capability. Whereas some other models like ANN, okay, and so on, actually you are not able to do this. So you need additional techniques, okay, to help you validate these models. Okay, so just now I think I mentioned about what is explainable AI. So the next one I will talk about is why this matters, right? So when AI become more advanced, so humans are challenged to explain how the AI model come to a result. So I will say the whole decision-making process is actually like a black box. So when you say about black box, means it's very hard for interpretations. So why interpretation is very important? So in the previous slide, I mentioned that interpretation is important because if you know what is happening inside, you should be able to debug and also further the improve the performance. But there are actually other objectives. For example, today you train a model, you are not really sure whether this model can be deployed to the production or not. So in this case, it got another features, which is that you want to raise the developers' confidence. Okay, today I train a model, I feel the accuracy is 99% already, but whether I can deploy this or not, actually I don't know. So there's another, okay, this is one of the way, means you can use the explainable AI technique to verify whether your models is it perform or do the prediction as what you expected or not. And lastly will be improve your user trust, because if your customer, okay, you go to a customer site and you tell your customer saying that, okay, I want to deploy this model, then he will ask you like, why you think this model can be deployed? Then you can give this the insight you got through the explainable AI. Then after that, these are going to raise your user trust, right? Okay, and next, I would like to cover how explainable AI results are normally shown. So according to my interpretation, is that there are actually 3 ways. So the first one is known as pixels level attribution. So what does the pixels level attribution means? That if today, okay, this is medical images. So if you got okay, so for example, this is, can say it's X-ray MRI. So after I get these images, then the doctor said that okay, you got the disease. Then the next question I'm going to ask is that, can you tell me which area of these images there is a disease? Okay, so if you're using the Explainable AI, instead of you just predict, because currently if you train a machine image classification model, it tell you whether this patient, based on this image, there is a disease or there is no disease, but you cannot actually explain why you think this image if there is a disease. It will tell you, it will highlight this region and it will tell you that, oh, actually there is a disease there. And secondly, instead of we study on the output, okay, you also can do it on the using the TensorFlow breakdown. So this TensorFlow breakdown is very good because it shows you the heat map of the neural networks layers from the TensorFlow breakdown, right? So you can see the operation inside each of the layer. So I would say this tool is very good, but it will need applicables or very interpretable when your ANN is very shallow. Okay, when your ANN becomes complex and complex, like deep, yeah, you can use the CNN very few layers more. Then probably this may not be a very good presentation, okay, for your exploratory areas. And last one is called Google What If tools. So this Google What If tools, how it works is that he's trying to do some perturbations, okay, on your inputs, and then you try to see how it goes wrong. And so what if means what? So if I try to change a little bit on this big value or what, so I want to see how's the result looks like. So so I think this is the purpose of the Google What If tool. So normally, this is what I can currently what I see. There are three ways of presentations. So one is through the images itself, and then you also can show the the representation inside the layers, and then you also can do some sort of like what if, okay, comparisons. Okay, and in terms of the categorization of explainable AI techniques, there are in the literature there are multiple ways for you to categorize. Okay, there are multiple groups. So today, I think we are going to cover a few algorithms here. So we are going to cover something line and also the sharp. So these two I'm going to explain with one works, and then I think the most common one currently is called feature attribution methods. It means it's actually doing something like this. Like for example, I got the image and then it predicted, yeah, there's a defects, no defects. If there's a defects, can you, instead of just tell me, because the model able to predict defects, no defects, can you tell me where is defects? So I will aim from that result, I manage to know whether my model is really learning the correct things on. Okay, so let's proceed. So what is feature attribution? So it actually indicates how much each features in your models contribute to the predictions for each of the given instant images. So this is an image, original image. So there's birds. Then you try to classify like, okay, is there a bird inside or not? So the answer will be yes and no, right? So the answer is yes. Then can you tell? Okay, so you ask the Explainable AI algorithm, say, can you tell me where is the bird? Okay, so it will highlight the region for you. So this type of algorithms, then we call it as a features attribution. They tell you which pixels contribute to the prediction the most. Okay. So in terms of the type of the feature attribution, currently there are two ways. So we got the perturbation-based methods, and the second one is known as a backprop-based methods. Okay. So what is a perturbation-based method? So the goal is actually to analyze the effects of changing the input features on the output predictions. So what that means that, so you want to study how this input feature change, okay, how it's going to affect the output prediction. So the process is like this. First, I got an image, and then I try to have a little change on the images. It can be different type of pre-processing methods and so on. So I try to have a groups of new images from my previous from my original images. So these type of images I will call it as a perturbation images. Then after that, I'm going to put these images into the model for inference or predictions. Then after that, I try to measure or the algorithm try to measure the difference from the outputs, original outputs. So from there, you're basically able to know which features or which pixels in the image contribute the most to the particular predictions, and it will tell you, okay, if for example, these images will be a dog. So what the algorithm trying to do is that, okay, is there a dog inside or not? Then you say yes and no. Okay, so if the answer is yes, then can you tell me, okay, where is the dog? So if he recognizes the dog on the face side, then you will say, oh, the model is really learning the same things. But if he try to highlight the region is somewhere background, so probably this model is not really learning. It's just learn from the noise basically. Okay, so what is so good is that for this category of the algorithm is that it can show if the model is overfitted or is really learning the irrelevant features. Okay, so the example algorithm includes and Sharpie value samples. Okay, next, this is the second category I mentioned just now. It's called a backprop based methods. So what he's trying to do is that he tries to compute the attributions for all the input features with a forward and also a backward pass. So the process is something like this. He tried to okay, so this is a forward pass. Then after that, he tried to backprop. He tried to track on the back, like for example, you predict these images is a dog. Then we ask why you think it's a dog. So you try to trace instead from the back, because when you do prediction, you are passing the image to the inputs and then you get the outputs. Now, if you try to run this algorithm, you try to go backwards. So you already got the result. Then you try to ask why you predicted as a dog. So from there, you try to track which feature contribute the most to the particular prediction. So this type of algorithm is called a backprops. So the good thing about this algorithm compared to the perturbation based is that it's actually run faster. Why? Because for perturbation based, you need to create a lot of the perturbed images or basically the additional images for it to study do the explainable AI. So that's why this process actually is much more faster. But of course, if you want faster means it's less accurate, right? So that's why these type of algorithms may not be that accurate compared to the perturbation based. And the example algorithms includes integrated gradients and also gradient. Okay, so the next I'm going to present you a few case study. So this is a first hands-on case study that I have done previously. So it's on the fruit classification datasets. I trained it on the ResNet 34 model architectures. So in terms of the distribution of the training and validation datasets, I got 3 classes. I got pumpkin, I got tomatoes, and then I got the watermelons. And then total images is around 600, and they are actually equivalent balanced datasets. Okay, each of them around 250 images. And I split into train and validation. And then in terms of the classification report on the validation datasets, so I get the accuracy weighted average is around 0.898, so it's 98% accurate. So regarding the confusion metrics on the validation dataset, as you can see, there are 2 images that are wrongly classified and the remaining are the same. So what I'm going to do now is that I'm trying to reasoning, okay, using the explainable AI algorithms. So what is go wrong or what is I want to check whether it's goes wrong or goes right. So I try to have 3 images where one. So for example, the first one is pumpkin images, means the ground truth is a pumpkin and it predicted as pumpkin. So all of them actually are the correct predictions images. And I got another 2 is the wrongly predictions. One is I purposely do it wrong because if you see the ground truth, I do it as a tomato. Okay, so this maybe happens. Why? Because when you try to if you're going to create your own labels, right? How do you show sure that your people who annotate the image won't make the mistakes, right? So if you're able to train a model something like this, so you may want to go back and see, hey, why this go wrong? Probably it's because your labelers are doing wrong. Okay, it's not the model itself. Okay, so this type of image, it may happen. Okay, and then the second one is the ground truth is actually tomatoes, but the model predicted as pumpkins. Okay, so these are the results of the correctly predicted original images. As you can see in these images, right? So I using different type of the algorithms. So I got saliency, And then I got occlusion. So occlusion is actually the perturbation-based algorithm, and saliency is back probes, and GradCam is also a back probe as well. Okay, and what is the difference between the layer GradCam and saliency is that layer GradCam you need to specify the layers, and normally people were going to take the last layer, okay, as the input of the GradCam algorithms. So these are the correctly predicted or original images. So as you can see, for example, this is pumpkin. Then you try to ask question like why you predict as pumpkin. So okay, if you look on these three images, they will tell you, okay, I actually focusing, okay, on this region. Okay, so the model actually focusing on this region. So this model is actually performing like what you expected. Okay, same goes to tomatoes. Okay, so you will see that these two is actually the different window size. Okay, okay, if you got a bigger window size means that it will perform the algorithm faster because of the sliding window issue. Challenge, because you want to have a clearer resolution means what you need more power lah. Okay, so okay, and then we got the same goes to the tomato and also the watermelon. So you see that actually trying to focus on the same side, but it's not that obvious. Okay, if you're using the dot, because like saliency, this one is I would say it's very noisy. But if you're using these occlusions, it seems like somehow show quite an accurate result. Okay, for the validations. And then in terms of the layer GradCams, what they're trying to do here is that so I got the original image is like a pumpkin, and then I want to see if my output is pumpkin, why you predicted as pumpkin. So he showed me actually I'm focusing this region, which is correct. Okay, and then I got the tomatoes and watermelon. So you see tomato, somehow he tried to focus a few pixels, okay, but not that much compared to the pumpkin. And watermelon is totally gray out. Means that if you say why you predict as watermelon, he don't give you a very, how to say, he don't really bother you. Okay, that's why he say black. He very sure that this region there's no watermelon there. Okay, so same goes to the tomatoes. So you see the tick here means the correct predicted one. Okay, so you see that it's very obvious model validations, okay, for these two. Okay. And next, these are the wrongly predicted original images. Okay, so I think we can just directly go back to this one. So if you're using the layer GradCam, you will see that the result is quite similar between the pumpkin and tomatoes. Means that in these images, the model actually very confused. Okay, they think that these two are correct. Okay, so this is one of the cases. So this one of the the conclusion you can meet. Okay, and then this one is totally wrong. Okay, so from here you can have a concluding remark is that seems like pumpkin and tomato, they are likely to mix compared to watermelon. I'm guessing because of colors. Okay, they look orange and yellow probably is more closer, okay, compared to green, right? So this may be the some hypothesis I can make. So from here probably I can after doing this probably I can do something else, okay, just to debug and also improve the process. Okay, and the next example I want to show you is on my one of my PhD work. I actually published this in just a small conference. Okay, but basically I'm using a lime and sharp to try to understand what is the operation inside. Okay, so how we are going to start is that actually I trained a model using a deep reinforcement learning. So what I'm going to do here is that I'm going to control these DC to DC converters. So this is a maximum power point tracking problem. So I'm going to have solar panels, but the solar panel may not work at the more ultimate rate, okay, because of the control provided by the controller to the DC to DC converter. So my role of my MPPT controller is actually to make sure that the maximum power can be drawn from the PV panel. So this is how the circuit design looks like. So this is how the curve are going to change. Okay, when my solar irradiance means that the strength of the sun. Okay, so if the solar irradiance is around 200, 400, 600, 800, and then 1000, actually the height is actually different. I want my models to able to to predict the action correctly here. So what are the observations? Means what are the things that what are the information we receive by my model before he provides these actions? So I'm trying to study, okay, the difference between I providing the duty cycles and also the no duty cycle. So what does duty cycles? So duty cycle actually is the action, okay, is a previous action I provided to the DC. Okay. So Vin stand for the input voltage. So it's the output voltage from the PV array. It's the input of the DC to DC converter. And then I got the Pin. Pin stand for input power. And then I got the delta Pin. Delta Pin is the difference between current power and also the previous power. Okay. And then I try to study the effect of this D. Okay. So this D is a duty cycle, but I also provide the previous duty cycle information for my controller to predict. Okay, so my action is actually a delta D, so it's a change of the duty cycle. So I'm going to either plus or minus, okay, my original duty cycle. So for my next action. Okay, so my role of the role of this MPPT is that he want to do something like this. Okay, so initially I'm at the rate that is not optimal. Okay, and then after that I'm going to raise my duty cycle until a place where it's more stable. So this state we will call it as a steady state, okay, conditions. So before reaching the steady state, so section 1 and section 2 is known as a transient response. So the section 3 and 4 is called as a steady state, okay, response. So from here, so my aim here is to study the contribution of each input to the deep reinforcement agent, because now I got 3 observations and I got 4 observations. I don't know which observation is, I don't know whether D is really important or not. Okay, from here, I want to study. Okay, and what I'm going to do is that, so this is the original control curve that I got. Okay, so for example, I take about 10 time step. You can think about 10 seconds or 10 milliseconds to achieve this control. And so I separate the whole process into 4 sections. So the first 2, section 1 seems like it's very far away from the maximum point. So maximum point means the optimal point. And then I got the second section, which is getting closer, in the process of getting closer. And then the third, and the section 3 and section 4 actually is already reaching the optimal point. So I want to see how these curves actually are varying, okay, under different sections. Okay, so this is the results of the analysis using the line. So for information, Lime's he's only able to handle single predictions, means that it cannot couple it as a group prediction, means that I cannot study the whole section as a whole. So what I'm going to do is that I'm going to print out, okay, or display out all the points at each time step, and I want to see what is the reaction. So as you can see in the section 1, okay, I think you all can focus on this. The first one is just a duty cycle, okay, the change of the duty cycle. So it's basically my output here, okay. So if you can take a look, section 1 is not that noisy, okay, and after that you go to section 2, then section 3 and section 4, it seems like it's very noisy, okay. So the first, second, and third is actually the ranking. So which feature is most important, okay? Among these 3 features, which one is the most important? So as the first, so the P in, okay, is the most important, means the input power is the most important. After that, when I reach a section 2, seems like the delta P in, okay, is getting more and more important. So he's actually trying to be fluctuating here. But if you take a look on this, if I added the information D here, you will see there's no fluctuation there. So you may ask, like, why? Because D is actually just my previous cycles, right? So if I'm able to remember this D, probably other feature is not that important. So my model is actually memorizing the D and ignore other features. So this is the insight, okay, when I use the line analysis tools, and then I found that my model actually is not really learning. If I provide the D, it's going to memorize. Why? Because if I manage to know the D, I will know which spot to stop. Right, okay, so because I already memorized it already. So this is how I get from the analysis result, okay, using the line. And another algorithm is called a SHAP, okay, SHAP. So I was doing the same, but So I got two results. One is from the observation with 3 parameters, and one is observation with 4 parameters. As you can see, the D for the 4 parameter one is always dominant, right? So you got a D here in the first section, the D on the second section, D at the third section, and also the D as the fourth section. So from this part, you're able to see that, okay, so D is a very important parameter, no matter how, okay. But if you look at this, okay, if I got the observation without the D, so probably, okay, the first section P in is the most important, and then P in delta starting to get more important. Why? Because I want to know when almost reach the steady state point, he will going to fluctuate. So I want to know the difference between the power, current power versus the previous power. So when I try to rise from the bottom to the top, actually my differences between the power is not that important. So this is the result, okay, if you can get through sharp and also the line algorithms. Okay, so these are, okay, the following one is the case study, I got it online. So these are the algorithm classification using the ImageNet datasets. This is the original images, and you got using different type of the explainable AI algorithm, you will get different results. For example, using line, and then you got the anchors, you got the CAM, and then you got the guided cam, and then you got the perturbations methods. So you're going to highlight to you which region these models are actually focus at when they try to do that prediction. So for example, this is a zebra, then it will tell you like, oh, why is zebra? Then it will tell you, oh, these are the regions that actually I focus at. Same to this one is a multi-label classification in remote sensings. He tried to explain the models, whether these segments is, these images is a urban fabric or is a forest fabric. Okay, so if you say, oh, it's a urban fabric, then you will ask like, why is a urban fabric, right? Okay, so which area you are. Okay, so these are the resource for if you want to go further for this topic. So I think because today is a talk, so I'm not planning to go through too many technicals. Instead of that, I actually present the result to you directly. Okay, so seems like I still got 10 more minutes. Okay, I think I can briefly go through with you on the algorithms. Okay, so when you go to Keras documentation, if you type on Explainable AI, actually you're able to see 3 tutorial guides. One is using model interpretability with integrated gradient. So integrated is one of the Explainable AI algorithms. And another one is called a grad cam. And the last one, if you are dealing with a transformer, so basically you got the attention model. So from here, you got attention head and so on. From there, you also can visualize it out and to see the importance. Okay, I think we can just slowly go through this. Can you see it? Okay, so we are going to have a setup. So this is all, okay, I load my images, then I initialize my ImageNet weight, okay, initialize my models, and then I put my image in. And so this is the image that I got. Okay, after that, then I try to implement the integrated gradient algorithms. So this is getting the image array. So we can just keep this. So he tried to get the gradients. Then after that, he tried to calculate the integrated gradients. So as you can see, the code here is very lengthy. So I think Keras is not really support very good on the explainable AI yet. So hopefully in futures we are going to have this one. Okay, and then we got a random baseline integrated gradients. So you want to have a random baseline for this one. So I think, then after you calculate all the gradients and so on, you want to visualize your result. So you got the gradient visualizers, okay, to visualize all the results. Okay, and yeah, I think you can skip this. What else? Okay, so we got visualizers. Okay, so I think this is a real code. So first I try to get the image first, and then I convert it to a NumPy array. Then after that I keep a copy, and then I pre-process it. So I do the model prediction. So when you do the explainable AI, normally you need to have a model first, and then you need to test your prediction result whether it's correct or not. Okay, if the prediction is actually like what you expected, Then the next one is that you are going to implement the explainable AI algorithm. So here is that first you try to get the gradient, then you try to get the integrated gradient, then after that you just try to visualize the images. So after the visualization, I'm not sure whether you can see the dot here or not. Actually, there are some green dot here. Okay, the dot here actually showing the pixels that the image, the algorithm focus at. Okay, so I think this one is on the Keras IO documentation. You can take a look later. And the second one is on GrabCam. So GrabCam is just another algorithm of the Explainable AI. So you all can go through it. I think I briefly go through. I think it's the same thing, just that he tried to plot the heat map. So pre-process the image, and then I have my model ready. As I mentioned, GrabCam actually is a layer based. You need to specify which layer you want to interpret. So normally we are going to take the last convolutional layers. Okay, and after that, we're going to show you the attribution. So this is actually the result where it focused at. But normally when you see this result, you're not able to predict because you were looking something called superimposed visualization. So it will highlight to you, if I say elephants, then where's the elephants? It will tell you somewhere there. Okay, and this is the result of the, he got another images called dog. So he tried to focus where's dogs. Okay, that's all. Okay, then the last one I think I will share with you today is on this vision transformer representation. Okay, we can skip this. So basically import. Okay. Data utility means that I try to load the image and so on. So this is my original image. Okay, and then I got my model ready. Then after that, I try to do inference. The step is actually quite similar, but you try to use a different different algorithm and so on. So mean attention means that you got all the transformer block. You try to find the mean, okay, for each for your gradients, and then from there you basically able to show something. So these are the attention distance. Okay, we can. So basically is a mean. Okay, just try to take the mean for all the attention. Okay, and the second one is on the attribution rollout. So because in transformer you're going to have probably you're going to have self attention layers. So from the self attention layers, so you also can visualize out. So this is the attention map. So you got the original input, and then after that, so if I want to plot the attention map out, so how it will look like. And the third one is called attention heat map. So instead of just show the self attention layers, you also can show the attention for each of the layer. So I think this is the result. So you got attention head 0, 1, 2, and 3. So you can show every layer if you're using transformers. Okay, and if you are using transformer, so you got additional item here called positioning encoding. So for this positioning encoding, so you also can. Oh no, I skipped this one already. Oh, that one is the fourth one. Okay, sorry. So the fourth one is more on the learn projection filter. So you also can display it, okay, in this format. So these are the features that learn by the transformer, which actually humans also don't know how to interpret this. Okay, but just show you. Okay, and then the last one is on the positioning embedding. So these are the position embeddings. Yeah, that's all. Okay, and of course, Keras. Okay, these are the three tutorial I can go through with you now, and then you can go for other documentation like TensorFlow Core. Actually, they got that's why I say they are lacking of support because they only support for integrated gradients. Okay, and then you got Vertex AI. Okay, so you can play with it for the Explainable AI as well, and then you got the GitHub, Medium, and also other blogs for you to learn. Okay, so I think this is my last slide. So as a summary today, I think for this 45 minutes, I have covered first is machine learning pipelines. So the main focus is actually for the model validations. Okay, then after that, I introduce to you what is explainable AI and why this matter and how explainable AI results are normally shown. And then in terms of the categories of the explainable AI, so in the literature, there are multiple ways to categorize it, but it's okay. I try to cover some. And then I mainly talking about, first one I'm talking about feature attribution. So we've got two types, perturbation based and also the backprop based. And then I present you 4 case study. One is my own Two is I got it from literatures, and last one I show you the resource where you can get it. So yeah, I open for question, and yeah, if you want to connect me through LinkedIn, welcome. Okay, thank you. Okay, yeah, question. Oh, can I walk now?
So you mentioned about Keras support for what other like or what other
Okay, so actually TensorFlow, they got some. If you go to this TensorFlow, actually they did support the integrated gradients. So you can either go through this or you can also go for PyTorch. Because I've used PyTorch quite often, so I'm using the Captum 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 library. So I think that is actually quite famous. And then yeah, I think there are other examples here. Probably I can take a look. So this is a Keras explainable model on the GitHub. So he actually allow you to load the Keras model as well. So yeah, you can do different types of the explainable AI. So like the yeah, currently I'm presenting a cam, and then we got still others. But this is not all, but at least some. Okay, so I think currently is not yet. It's not really a. I don't see the very full features on this yet. Okay, thank you. Only got one mic.
wonderful. So how do you like
You mean scale it for explainable AI?
yes.
Okay, so normally when we do the explainable AI, right, we will do it normally after we train the models, and then we try to do on a few images. So we currently I don't have. I mean, even in my case, currently I not really go through every images. I will just pick some images that I feel is hard samples, or probably is easy samples. Definitely you are going to pass lah. So probably you may want to know. So you are going to take a rare cases. So for in my case here, right. So if you take a look, so how I sample the image is that okay. Yeah, I mean I will going to have a lot of the correct prediction case. So definitely I'm not going to take all. So what I'm going to do is that okay, so a few class. So I'm going to take yeah probably one or two from each of the classes, and then what I really curious me is that actually the wrong prediction one. I don't know what is really learning. So sometimes it's either human is making mistake, or probably is really the model making mistake. Because for the pumpkin and tomato one, honestly speaking, I don't know what I want to do because, for example, this one, right? Okay, if you take a look on this, actually, I don't know how I can further improve it. Okay, for this case, right? But after I compare for a few wrong images, I managed to come up with a decision saying that the pumpkin and tomato they might be easy to get confused because of colors. Because if you're thinking about watermelons, okay, it's totally yeah, it's not in the list. But if you see pumpkin and tomato, probably they are in the same color. So I'm guessing this is what is going wrong. So I think you are very easy to validate it. So either you put more pumpkin and tomato image into the model so that you get more correct confidence, or definitely cannot change color lah because pumpkin can change color, right? So I think it's a real world lah. So I think this will be my solution if I face this problem. Okay, what else? What else? You mean what is the difference between explainable and the interpretable models, right? Uh-huh. What type of methods we use? I don't really understand what is the question. Hmm? Huh? You mean how it works? You mean this slide, right? This one, this one, this one. Oh, okay, it's like that. Normally, when we're talking about interpretability, like it's talking about the model itself. So the model itself means that decision tree have a higher is more interpretable because it got the function, okay, to do the interpretation by itself without additional algorithms. But when the algorithm getting more complex, for example, random forest is still decision tree, but it's a lot of trees inside. So it's getting less interpretable. Okay, so this is the context of the interpretability. So normally when people say I want to do explainable AI, they are actually focusing on this algorithm because itself it don't have it don't have the capability of interpretation. So that's why you need the explainable model to come. Okay, I think I repeat again. Interpretability, I think I don't use the interpretable. I think I use intrinsic. Intrinsic means that model itself has its own capability to tell me what is going on. For example, decision tree, they're going to tell you if this happened, then what? So the model itself already got the explainability interpreted. I mean, how do I say? Got the explainable feature inside already. But when talking about A and N, you just see on the weights and then you see on the bias, weight and bias, but actually you don't know what you can do on it. Except transformer, because transformer you can print the heat map out, right? But if you don't print the heat map out, never you cannot know what's going on. mm. Mm. Mislabeled tomatoes. Okay. This one. How I know there's an error there? No, I just print all the models that I think is wrong prediction, and then I look at it. Yeah, currently yes. I don't see an automatic. How can you know that? Oh, this is human label. This is a prediction. But unless you got a label cleaning process. Yeah, I mean this is another topic. It's called label cleaning. Auto label cleaning lah. But currently no. I don't have any experience on this one. So normally when troubleshooting, I will go manually for this. I think one. Uh huh.
Think that as AI advisable to do.
I will think yes, but it requires certain knowledge. Why I say so? For example, this image, right? If you're talking about user, he will say, oh, these two, I see these two image, but the analysis you're coming out is different. You see these two image, no meaning. But if you are experienced enough, you see on these two image, and you see on these two image, you will likely guess what is going wrong. So you still lack of I wouldn't say lack of understanding lah, unless I'm thinking of probably in future ChatGPT are going to, okay, you give them this is a prediction, this is a ground truth, and this is prediction, this is ground truth, this is prediction, and then you give the ChatGPT and say, can you tell me what's going wrong? Probably one day I'm thinking of ChatGPT probably can do it but currently I think you require reasoning. You need required reasoning. Yeah. Okay, that's all. Okay, thank you very much.